Ivan, or
Oh, thank you. I said I was going to do that. Thank you for whoever
Ivan,
started
you
that.
can keep going.
Thank you. Um, okay. Yeah, so my name's Ivan Rodriguez. I'm the Technical Programs Director for the Canada chapter. Thank you all for joining. Today, the topic is when malicious actors control your subsystems, a systems engineering approach to functional perseverance. We have two presenters for today's program, and just this is a sneak peek to something that you will find in the INCOSE Insight magazine. So ask good questions, and you may inform what gets put into print. So our two presenters are David Hetherington and Ivan Taylor. David Hetherington comes to us from Austin, Texas. I don't believe that's what's in the background, but
No.
in your video, David. David's from Austin, Texas, and comes to us with over 40 years of experience in complex systems and organizational transformation. David is currently a principal at SSI, where he assists clients with MBSE and team skills to serve a broader digital engineering organizational transformation. David's a member of the SAE G33 committee and currently working on updates to the Configuration Management Standard Implementation Guide. He's also a member of the SAE STPA task force, contributing heavily to the recommended practices for applying STPA to system security. And by the way, STPA refers to System-Theoretic Process Analysis, which will be discussed in today's presentation, together with System Dynamics, or SD. As an aside, David is multilingual, fluent in English, Japanese, and German. And David came to this call right on the heels of another call that he had with Japan. Speaking Japanese, no doubt, David.
Correct.
Ivan Taylor is the president and senior researcher at Policy Dynamics Incorporated. Ivan has his master's degree in information and systems science and a PhD in public policy. Ivan has served as a peer reviewer for the social systems issue of the Insight magazine and has delivered various INCOSE International Symposium presentations. Ivan has also provided several presentations at INCOSE's International Workshop for the social systems and the resilient systems working groups, as well as multiple presentations at other INCOSE Canada chapter technical events. And Ivan is a board member with the INCOSE Canada chapter. So with that, I'm going to turn it over to David and Ivan. I'm going to mute. One last comment before I turn it over is we have a pretty small, well, not too large a group here, so it's probably okay to just unmute and ask questions. But
Yep.
I'm going to defer to David and Ivan as to whether you want to complete your presentation first and entertain a Q&A period at the end, or are you open to questions during the presentation?
I like questions during the presentation. It actually makes the presentation a lot nicer. So go ahead and ask.
There you go. We've set the rules. So if you do have questions, maybe what you could do is raise your hand just to give the presenter an alert, and I will also watch for that.
Right. Yeah. If I don't see that, remind me that someone's got a
Then
question.
just interrupt if need be. But
and that's my section. And Ivan's going to do the section. Ivan, do you prefer to have the questions at the end, or are you okay to take them as they come?
yeah, I'm okay. I'm okay with either.
Yeah.
Okay.
Okay. So
Okay.
we're both fine to just take.
So David, please take over the screen
Okay.
And begin.
Yeah, so before I do that, I'm just going to talk a little bit, like a minute or here before jumping into slideware. And so, yeah, I'm actually done a lot of functional safety, and I've been working with the Army, had been working for a few years. The question was MBSE and cybersecurity. And this led to a document very short document done by the Air Force, DEO's best practices for cybersecurity, in which they noticed that there were over 23,000 pages of guidance from the DoD on cybersecurity. In other words, there was no guidance. And they quickly went through some of the things people had been doing, like, red team exercises, and explained why that really didn't work because you could never pay the guys enough to keep them around, and suggested STPA. And I was aware of STPA, and so for that week I really got into it, and I've been working on that. And what I'm doing in the STPA work task force is helping update the best practices, SAEJ 3187. We're making a 3187-4 appendix on cybersecurity, and I've been working with William Dollar Young, who's the world's expert on this, and helping to write the text on that. So that's the background. And when I came across this article, we're going to introduce briefly. It originally was in '82, and it was published by the guy who invented LaTeX. Some of you people who are formula formatting geeks like LaTeX for academic. And that guy was at Stanford Research Institute, SRI, and he invented LaTeX, and also put out this paper, which he called The Byzantine Generals Problems. And he only called it Byzantine just to avoid picking any country where that still existed. He didn't want to offend anybody. It previously been, some people referred to as the Chinese generals problem. But in like late last year in an IEEE magazine, there was an article from someone in that area saying, hey, actually, really the real Byzantine Empire was kind of like this, and went over the history of the intrigues in the Byzantine Empire. And that made me aware of the article. And I got intrigued because we're going to see this is a kind of a peer-to-peer self-regulating system. And one of the problems we're having, the big problem for the DoD, is all the existing cybersecurity, the bulk of them are checklist oriented. Go down a list of literally 800 different controls and see if they all work. And this is important work, but it doesn't do anything for you if the attacker's already inside the system. And that's one, and everyone's aware of that in the DoD. And the second thing they're aware of is what the generals really want to know is, okay, I'm under attack, or maybe I'm compromised already. Can my system complete its mission? Which is really a resilience thing. So I started looking at this and I said, let's take that example and let's look at it from an STPA. And I was aware of System Dynamics. My boss is a big fan. I knew roughly what it was, but I'm certainly not an expert. So I proposed the paper, and then went looking for someone, and I had met Ivan before. I knew he was into this, and I approached Ivan to take the System Dynamics half of that. So we're going to show you what we came up with, or what we've come up with so far. It isn't a fully polished, all worked out thing, but it's more of an exploration of those two different angles looking at this problem, and an example of how you might implement something in that, say, an auto that to do it. So with that, I will now take over here and share. Okay, and now does everyone see my screen?
Yes, we do.
Okay, and I'm gonna move the taskbar out of here so it's not distracting. And this beautiful picture on the front, that's Ivan's working, did that. Okay, so yeah, and as I mentioned here, this, security is essential, of course, for everything. And we're really looking at functional perseverance. The machine keeps going. And in fact, one of the elevator speeches I use for the desired end state is a car driving in the rain. So, or the car is driving down a highway, it starts raining. The rain is a kind of attack, adversity. So the driver reduces speed and activates windshield wipers and activates headlights, but doesn't stop. The car keeps going even during the attack of the rain, right? This is really what the leaders in defense want to see about cybersecurity. That isn't the case today. You either keep the enemy out, or once they're in, you just die. Even though there have been attempts to do cyber resilience, they're not very far along. So this was what we were going after. And yeah, and this is more of this, right? Detection. And this is where you're really thinking about how we design it so it will work even when corrupted from the inside. Okay, so here, this was the original thing, that we're going to show you the idea in a second. And the author of the original 1982 paper was writing about this metaphor of Byzantine generals communicating. But of course, this guy was a computer science guy, so it was really just a metaphor for a network-driven consensus algorithm, and in which some of the nodes might be corrupted. And so this was set, and then there have been multiple PhDs written on this since. We certainly haven't done a PhD, but this was the original problem. So we have an enemy, and we might imagine a siege, or where we're surrounding the enemy, and we've got multiple generals around. And as originally formulated, the transmission links are secure, so we don't lose messages. We get them; they do get there. And the task at hand is to coordinate. We're all attacking, or we're all going to retreat. Every general's getting the observations, which they're hopefully sharing. Some generals might be corrupted. One of the other things was very interesting in the original paper, reflecting the state of network communications in 1982. They basically assumed that network communications were extremely expensive. So each general would really only be able to communicate with its, say, two or three nearest neighbors, and you wouldn't have an any-to-any, which turns out to be no longer true in many systems. So that has altered the problem in our analysis of it. But so this is this, and what the paper proved was that if you had essentially at least 2/3, I think, of uncorrupted generals, this thing would survive. And here's what we just said without that. And they also introduced a wrinkle without really explaining it very well. Suddenly they were talking about one of the generals being the commander. And they went on to show that even if the commander is corrupt, the thing would survive if it had this kind of consensus algorithm in it. And that was kind of interesting. So this is what we started with, and we looked at this. So, okay, so we have a commander with the two nearest generals and subordinate generals here, and local brigades. This is kind of how the problem was described. So, you know, this is what we're saying is that currently malicious actors are not just trying to disrupt things, they're often trying to take over control of it. And we're trying to make a design that can deal with that. The thing's still running. It hasn't stopped running. In fact, it may seem to be running smoothly, but it's maliciously doing the wrong thing. And maybe multiple of them are doing the wrong thing. So we taking a step toward where we want to be, we think of, well, maybe we have a master controller and we have subcontrollers, and we haven't defined this topology just yet. And each controller has some actuators and sensors, and there's the physical system in the environment, and this is kind of what we're looking at. And the first thing we notice is any kind of hierarchy is going to be problematic, because if you take over one of these red nodes or the master controller, you're dead, right? The whole thing dies, or at least a huge chunk of it dies. So we probably don't want a hierarchical approach. And these days, that original constraint really isn't there, especially if we're thinking about something like a combat vehicle or a car or an aircraft for that matter. We can have gigabit or even 10 gigabit Ethernet. And so we've got a lot of bandwidth. And we really can have a thing where anybody can talk to anybody. And if we then go to the software side and we use a microservices architecture, a publish-subscribe type architecture, everybody can listen to everybody. So you get a fully transparent, modern technology can make a fully transparent thing where everybody can see what everyone is doing. And they just subscribe, and they know when something's addressed to them, and they take action and respond. And they also publish what their sensors are saying, and so on. Completely feasible in a current thing. And we can take advantage of that in terms of a system design. So one of the things we can see also, if we think about like sensors on a car, we may have a sensor in the middle of the front of the car that's designed to look 200 meters straight ahead. Then we may have sensors on the corner that are designed to look over kind of maybe 180 degrees at the corner of what's going on. But those sensors, the corners and the one straight ahead, actually have what we can think of as peripheral vision. They can see some of each other's field. And particularly a phased array radar may have a very narrow beam, but for most part, you may be just having that beam sweep only plus or minus 3 or 4 degrees, but you can make the phased array beam scan, scan all the way to the left like 45 degrees and see at least some of what the other guys, the corner sensor sees. So you can snoop on what there is if depending on how you set up the system, the sensors and actuators can be designed to overlap a little bit and have some ability to confirm what each other are doing, or at least partially confirm it. Also, they can all listen to each other's messages and can see what each other are doing. And so for example, the one is the master tells the steering controller, turn left, and the steering controller says, yep, I'm turning left, but everyone else's sensors can see we're not turning left. The other guys can identify something's wrong with this guy, right? This guy's either inoperable or corrupted. It's not doing what it's saying it's doing. So leveraging this is an opportunity, right? So this is the essence of our design. So now we take a kind of the STPA look at this, and this isn't a full STPA workup, by the way, but the first thing we do, the first step of STPA is we start with what losses we want to prevent, and then we define hazards that could lead to the losses, and then the last thing is we identify system constraints that we need the whole system to maintain at all times so that we cannot get into the hazardous state. This is the base idea of STPA. And this is system dynamics. And here, system dynamics, my impression of system dynamics is it's a graphical set of a system of differential equations. All the things can feed into each other, and we can create very complex interactions of things, feeds, and effects and feedback and so on, and can be used to model tipping points and so on. So here then we're going to do redundancy. Certainly we're going to have some redundancy, but just redundancy, as we're going to show in a minute, redundancy of identical components doesn't do anything useful for cybersecurity. So we really need fallback components that are diverse. So for example, here, if we have three components, A, B, and C, and our system is just a straight flow through, if we knock out any one of these, we're dead, right? Because we're blocked. So you might say, oh, the traditional safety thinking would be, oh, just make them all redundant. We put a second set of A, B, C right next to the primary A, B, C. And if any one fails, we just use the redundant set. And this is the core of a lot of safety engineering, especially for larger systems, and things like ships and stuff do this all the time. And to some extent, aircraft do it, although weight is a consideration. The problem is this doesn't do anything useful in a cyber attack, because if the cyber attacker has figured out how to crack B, the cyber attacker can crack both copies of B. So you're not going to get any benefit of just having a second copy of B hanging around. So you need diverse redundancy, and of course we want to avoid a single point of failure, and we want to do functional reallocation. This is another point of resilience. The resilience, Scott Jackson from the Resilience Working Group talks about the real case is the United Airlines jet lost its tail and crashed in Iowa, and that the pilot figured out on the fly how to steer the aircraft by using the thrust of the engines. Apparently, at that time, no one had ever thought to do that. The pilot made it up on the spot, and was able to save at least about half the people. Still, there were some losses, but it wasn't a total loss because the pilot was able to bring the plane in somewhat under control. That's functional reallocation. The function was reallocated from the tail to the engines. And this is the dream, how do we set up from a resiliency point of view to do that? So one way to do this is, okay, so to get back to the cybersecurity weakness, instead of A, B, and C, we put A prime, B prime, and C prime, which do the same thing, but have a different implementation. Preferably a different kind of microprocessor, a different programming language, a different middleware stack, and so on. And you put them right next to each other. And now it's much, much harder for the cyber attacker to take out the whole thing, because if the cyber attacker takes out B, then the A prime, B prime, C prime thing can take over, and the cyber attacker will have to do an entirely different set of research to figure out how to crack B prime. So this improves your resiliency, but it's really expensive. Not only do you have to duplicate all the development, it takes a lot more coordination than standard software to make sure these things really do the same thing the same way. It's extremely expensive. And this kind of thing, I think the space shuttle had three-way voting logic, and it was an enormous cost for them, and the source of a lot of launch delays when the three computers couldn't agree on what was going on. So these are the differences: different programming language, different operating system, different communication stack, different physical processor, different design teams and different organizations. These are the ways to get the resilience from diversity, but they're all expensive, every single one of them. So another way that's a little more realistic is we slightly over provision A, B, and C, and we have each one host a somewhat shrunken version of another one. So A hosts a little backup copy of C, but it's C prime, not C. So it does at least the key functions of C, but in a different programming language on a different processor and so on. Hopefully you just make these three all have different operating systems and processors from the get-go, so that they're naturally all on different one. And B hosts the backup for A and C hosts the backup for B. This is a little more affordable from a bill of materials cost and a development cost, and gets you a lot of the benefit of the completely redundant approach for a much lower price. And if you really want more resilience, you can think about then going down to a second layer of that, where C prime is still, pretty big piece of C, like 80% or 70% of it. And C double prime, hosted on a different mode, is really just barely alive, crawl back to home level of backup for C, but there is some additional backup. So this is a strategy of providing tiers of backup at a moderate, of course, the cost is going up, but it's not escalating by tripling or quadrupling. It's just increasing the cost, say 20 or 30% usually. And looking at the network itself can have this. For example, in an automotive world now, many, if not all the chips, especially the microprocessors, but many sensors and other chips have ready to go ports for Ethernet and for CAN bus. And these two things are wildly different. CAN bus tops out at about a megabit or think, but you can still get a lot done on CAN bus, and Ethernet's much bigger. So CAN bus can be you got it there anyway, so you don't pay any extra for it except for the cable harness, and it can be a functional backup for the Ethernet if somehow the attackers manage to disable the Ethernet. So here we got this is how we're going to actually do this. Okay, so today's automotive microprocessors, and by the way, I should mention that, automotive microprocessors, what about airplanes? And well, I work with one of the top automotive microprocessor, and they run a charity called Multi-Core for Avionics for the aircraft industry, because the aircraft industry builds numbers like 50 planes a year, which are just silly for the semiconductor industry. So basically, most of our hardened systems are, or a big portion of them, like our combat vehicles, have little green boxes in them, like Curtiss-Wright. You peel them open, you've got an automotive microprocessor in it, because they're the only thing built at scale that's appropriately hardened, that's got long life cycle provisioning, and so on. Okay, so that's actually automotive microprocessors are powering all kinds of things for this reason. And they typically they now come with a lot of cores. 6 and 8 cores is not unusual. So we think about A, B, and C, we provision 8-core microprocessors, and we can put a VxWorks or a real-time OS in there, or multi-core OS, and we can allocate 5 of the cores to the primary function, 2 to the good backup function, and 1 to the weak backup function. So this is a very plausible way to implement this scaling backup in terms of this. And could you have a 5-core microprocessor? You absolutely could. And would it be cheaper? It would be cheaper, but you wouldn't have any redundancy benefit. So by picking a slightly higher price point part, and with a little bit more power consumption, not much in the auto industry, you can have enough capacity in your microprocessors to host these kinds of backup things. So here, we're, this dynamics is, what we're talking about. So here we're back to the STPA view now. STPA thinks of everything as control actions and feedback, maybe several layers deep. And this is the classic STPA control loop. And the definition of what the control process is usually quite a bit different than what the hardware designers think it is, because we usually include the human as the top level controller, like the driver of the car. And if we consider the driver of the car has a control algorithm. It's got a steering wheel that can go left and right, and brakes and accelerator. So, and the driver of the car knows how to run that control algorithm. Meanwhile, the driver of the car has a process model that's actually 3 pieces of that. One is a model of the world. This is a car. This is a highway. Cars run on highways, so on. And this is how the world works. Rain happens. So the world model of the is part of the driver's model, and then there's a model for what state are we in. Our car is currently on a highway, driving on a highway at 60 miles an hour, and it's dry and sunny. So that's the states that's in there. And then the third thing is input and response to input. Okay, we see something on the road, better slow down. And that's the control algorithm to do that. So we think of the control and there's control actions like the steering changes, braking or accelerating. And this control process is the whole car in that case. And the feedback is, of course, what the driver sees, but also the driver has haptic feedback. They can feel the car bumping around like we ran off the road or we're run over a warning strip. And they can hear things too, like sirens outside the car. So all these things are feedback. And the essence of STPA is that most, if not all, problems occur when something doesn't work right here. Like the control actions are issued, but they don't work for some reason because something's failed down here. But most often, what the STPA people are interested in is everything works right from a hardware point of view, but the process model, the controller gets confused for some reason and makes a so-called unsafe control action. And this is also thought of in this. So now when we're looking at our proposed system, we're going to have a voting system for these nodes that are spying on each other. And basically we're going to have 2, and now we're just voting, the process we're controlling is the thing to prevent the other systems the system from being corrupted. So on any one node we're controlling, we have continue operating or shut down. And we're going to show how to implement that in a minute. And we've got various kinds of feedback. So we can see what instructions are flowing to the element. We can see what the element's responding, and we can peek around the corner at the element's behavior various ways. So now we have an ability to make a control process to manage the potentially corrupt elements. So how would you do that? Well, one of the things we can do is we can leverage what are called watchdog timers. This is a classic thing in embedded software designs. And usually the way it works is the processor has a watchdog timer, and the software has to go tag the watchdog timer like every 500 milliseconds. And if the software fails to tag the watchdog timer, the watchdog timer determines that something's terribly wrong with the software and forces a reset. So this is very widely available. All kinds of microprocessors and chips have this available. And you can make a voting watchdog timer in which, say we had A over here, and we have C, E, and G are watching A to see if A is corrupt. The way that would work is the thing supervising would just keep tagging. Now you'd have a kind of an AND gate, just a little bit more complicated circuitry to make a three-way voting watchdog timer, so that C, E, and G would have to keep tagging that to keep the thing running. And then you would decide in your design, if you had three elements watching, do we restart this thing when only two do it, or do we wait till we get down to one and restart it? So this would all be a system thing, but any of the things, including the top controller, could work this way. So basically the the followers could be watching the controller, and if the followers, as described in the original 1982 paper, if the followers concluded that the top controller is starting to behave erratically, they could force the top controller offline, or at least restart it, or in a severe case, force it totally offline and fall back to the backup copies of the top controller that were distributed throughout the system. So this is the gist of our idea of how we would implement the Byzantine generals' voting algorithm to keep tabs on each other and do that. So next, we're going to go to the system dynamics. I'm going to turn it over to Ivan. But before I do that, does anyone have any questions? So, okay, Ivan, do you have your own copy of this up, or?
No, if you could turn my slides, that would be great, David.
Okay, great. Just tell me when to progress, right?
Okay, so yeah, like David said, he asked me to work with system dynamics on this problem. And so I tried to develop a bit of a synthetic case study. And we're going to talk about a number of things in the case study. And one part of it is the investment in fallback capabilities. And basically, we're going to talk about various different budget allocations. As David said, these fallback capabilities could be expensive. And so we have to try to optimize our investment. And so you can turn the next slide there, David. Okay, so anyways, we consider the cost effectiveness of these redundance measures, and then we're going to track resilience over time with system dynamics. Okay, next slide. So here's my simulation. It's the setup of the simulation. I set up 50 primary components, and they have various ranges and costs and capabilities. And when the 50 components are totaled up in terms of the cost, they add up to about $276,000 for the 50 primary components. And then I simulated 50 backup components or fallback components, which were much cheaper. So you can see that the primary components are between, say, $1,000 and $10,000 each. and the backup components are between $100 and $200 each. And you can see that the primary components have a very high capability, over 99% capability, and the fallback components have between 10 and 20% capability. So they're much less capable. But we can have many backups for a particular primary component. So you go to the next slide. So what I did is I did an optimization, and what I did is I tried to find the mix of backup components or fallback components that would get the maximum capability improvement over the primary set, with the minimum expense. Well, anyways, basically you can see that that you can get a lot of capability improvement with a minimum amount of money, and then eventually it starts to reach a plateau where you can invest more and more money and get less and less additional capability. So what I did is I took three scenarios. I took a $50,000 budget for um, uh, for the uh, for the backup components, and a $100,000 budget for the backup components, and a $150,000 budget for the backup components. And then I put those backup components in with the primary components in a very complex configuration. Okay, you can go to the next slide, David. So then I modeled an attack, and the attack attacks all the components, both the primary components and the backup components. And then I analyzed how the total system of all 50 components with the backups can respond to this attack. And of course, the obvious answer is that higher investments in backups improves the post-attack capability and recovery. So I used System Dynamics to simulate this post-attack capability degradation and the recovery. So now you can go to the next slide. So the idea is that the recovery takes time. There's security assessments and repairs to introduce delays. And there's also this tipping point, as David mentioned, where the system stability shifts from resilience to failure based on various investments in backup components. Okay, the next slide. And here's the results of the System Dynamics simulation. And you can see that it's a little hard to read, but basically the blue line is the $276,000 set of primary components with $50,000 worth of fallback components. And you can see that the attack basically causes that system to basically fail. However, there is an ability to recover after a while, but it doesn't recover to the full capability. And the $376,000 is the $100,000 investment in backup components. And you can see that this can persevere a little bit better, well, quite a bit better. It reduces the capability down to 20% after the attack, and the recovery is quite a lot more significant. And finally, we have the $150,000 set of backup components, and we see that this does even better, that we end up with about 36% capability at the bottom end, with an increasing back up to almost 95% of the capability after the recovery. Okay, next slide, David. I think you can carry on, David.
Right, yeah. So this is the point, right? As we're still adjusting and working on these simulations and models, but obviously you get what you pay for, but a layered investment, we think we can get a very good resilience and ability to identify attackers within the system and take them out while the system's still running, with reasonable additional system cost, perhaps 20 or 30%. With no need to triple the price of the system. And it isn't just a question of tripling the price. If almost any kind of engineered system, like a vehicle, a plane, or even a ship, you wouldn't want to triple the components because the thing would get heavy and you'd run into other problems. So moderate investments in additional power cost and so on should be possible to make this kind of thing by using this diverse backup strategy and having a large set of everybody watching each other and making sure each other seem to be doing the right thing, right? And this is then, we think, is the inspiration we've taken from the Byzantine generals to this. Well, in our conclusions, of course, security has to be built in, but and STPA and SD can do this, but we think that these sorts of techniques can be used, and we hope to do more going forward, especially with SD, to look at how we can use that to analyze the cost effectiveness of beefing systems up to make them more resilient. So that's pretty much what we had. I think that's it, right? Oh yeah, just questions. Right? Oh, I didn't catch the second misspelling of my name.
Sorry, David.
But questions, comments?
Yeah, very good presentation, guys. Thank you very much. I'll kick things off with a question. So looking at your presentation, so you mentioned 8 core processors, et cetera. So you are talking hardware implementation in that sense,
Right.
but the diversity, I think, is really for the software. Is that correct, for the application?
Well, okay, so the question, even in automotive space, you could have, you've got a number of different suppliers. So you could have NXP, Infineon, Texas Instruments, Renesas, and maybe a few others. So you could make the hardware diverse.
So you
And
could
then
get
you
some
make,
diversity there, yeah.
and when you do that, well, these days, a lot of them are running on the same ARM cores. So you have to be careful how you do it, but you can make both hardware and software diverse, I think.
Okay.
With some careful design. And and if it's unaffordable, you just don't make that piece diverse, but you acknowledge it as a risk and think about how to mitigate the thing that you can't make diverse, right?
Right. Further to that question, and I see what you're saying. Yeah, you could find different suppliers, for example, of componentry. In your earlier slides, when you had A, B, C, and A prime, B prime, C prime, etc., I recognize it was really logic that you were trying to illustrate there, but I couldn't help but be drawn to the serial nature of A, B, and C, and so a concern would be. If you did have a hardware failure, if this were a data path, a physical data path, if B failed, that could interrupt your flow. Now, am I misinterpreting? Is it purely a logic that you're trying to express here, or
playing fast and loose here? This is more of a dependency chart, right?
the dependency?
Say if you lost B, then these guys would take over the function of B, and there would be a path to C somehow.
Right.
So the point is more of a function flow, right? And the point, and of course, if we're really on a hardware architecture like this, then we really can do that, right?
Yeah, absolutely.
Yeah. If this guy goes out and these other guys have, the prime versions for that person, for that thing, can take over. Now you've lost some of the actuator and sensor because this guy's totally fried. But these guys who we sort of assume may be physically in full physical proximity may be able to take over some stuff. And we look at vehicles having, for example, camera, radar, LiDAR, and ultrasonic sensors for different purposes. Like parking is usually an ultrasonic sensing. So you may be able to get, some reduced function by, for example, having the ultrasonic sensor give you some help, even though your radar sensor is gone, right?
Right. Yeah, that makes sense. Yeah, and I see it a little more clearly here, where it's expressed more as a parallel. Parallel functions. But yeah, thank you. Are there any other questions?
Are there no existing systems that do something like this like the wireless communication cellular providers, where they have a what do you call it? An active and hot standby, where
Mhm.
if when a system goes down, the other system just kicks in. Because I
Right.
know that's what the wireless providers do. Um,
Yeah.
they're not located in one town; they might be another town.
Right. So the I started my career doing telephone systems, so actually pretty familiar with that space. And yeah, we when we built telephone systems like for airline reservation centers, uh, we actually built the system so the processors were redundant with a common I/O bus, and then there were two complete switch matrices, two DC power supplies, and they used watchdog timers and two of everything, right? In that, and and quite often that got you to about 5 nines, which are used for like call centers and credit card processing, and that meant 1 hour of unplanned downtime in 20 years. But then I worked with SAIC, the former Bell Labs, for the 800 number thing. They wanted to get to 6 nines. So by that time, we were using blade computers, and the racks of blades had dual power, dual everything. And then they put two of them in a rack and two in another rack next to that with a completely redundant. And then they put another whole set 500 miles away. In case you had a flood, and Houston had a flood and took out the center, and they got down to the 500-mile away backup. So this redundancy stuff, especially in the wireless providers, the telecom space, they're really used to it, and they get fantastic availability from physical failures and storms and stuff by doing that. But what it doesn't do is protect you from malicious cyber attacks. Because if your attacker wants to take down your network and you've made everything identical, then the attacker only has to crack one of them. And then after that, it's like shooting fish in a barrel. They just infect all of them and take you offline. So the strategies used by wireless and telecom providers, the pure just do it everything purely redundant, isn't isn't as good for cyber attacks. It's great for reliability and safety, not so good for cyber attacks. Does that help?
Any other questions, comments? Does anybody have any examples where you
Yeah.
have applied any of this theory?
Yeah, I'm curious to know if ever anyone's working on any kind of system where the stakeholders, aka management or whoever, is starting to complain that I want the thing to keep running even though it's being hacked. Has anyone seen that request?
Yeah, I see it in a primarily in a defense, but not only defense situation where we're providing positioning, high precision positioning and timing solutions and jamming. So a malicious actor who would jam the GNSS signals, for
Yeah.
example. How do we overcome that? And there's various means. The company I work for, we also we're in the autonomous driving space, providing positioning again, but paired with multiple sensors, as you had mentioned, David. And again, malicious actors can be a problem there.
Yeah, the redundancy idea, that's interesting. And I had the pleasure when I was working with the automotive semiconductor company a few years ago, and they weren't going to make the autonomous vehicle, but they wanted to have a good idea of how they would work so they could be sure they were making the right chips and firmware and stuff to go with the chips. So I had a several-week engagement with Edge Case Research, who's a spin out of Carnegie Mellon. And they laid out the following scenario of how their point of view, a safe autonomous vehicle works. And so in their way, you have the super brain, And the super brain is you're driving down the highway, and they mention the same problem. You know, two identical things doesn't buy you anything, because if
Right.
even if the it's not hacked, if the algorithm has a mistake, both of them will
Both of them do.
have the same mistake, right? So okay,
It's,
so they have super brain. So super brain is driving you from you know, Detroit to Toronto, and it knows where the Starbucks is and the Horton's donut, you know, coffee and donuts, and it's managing you on the highway. It's doing all that stuff, and it's using whatever AI and neural networks and great stuff. Meanwhile, they have another controller, and the second controller's only job is constantly think about the next 10 seconds. How are we going to get off the highway? And so it's constantly just planning. How are we going to get off? How are we going to get off the highway? How are we going to get
exit strategy? Mm-hmm.
Yeah, exit strategy. And then
Yes.
we have the third controller is a pure physics controller. So just doing Cartesian logic or trajectory looking, no AI, no neural networks, anything. Are we going to crash into something?
Mm-hmm.
Right? And then the fourth controller is watching all of this. And if it notices that the Cartesian logic controller and superbrain don't agree, it cuts their power and tells the emergency controller, get us off the highway.
Mm-hmm. Yes.
Very, very interesting, but a little bit different, but in the kind of in the similar vein, right? That you've got some mechanism in there deciding that superbrain is not doing the right thing, and so on. And even in the automotive space, even conventional automotive space, you've got a lot of that kind of thinking. Like in your ECU, you have a microprocessor there, and it's got a watchdog timer and it's restarting. And meanwhile, you have a chip there to provide power, and it's got to take messy, ugly power from the car battery into which has got all kind of ringing voltage and stuff in it, clean it up and make 5 volts, 3 volts, 1.2 volts, 0.9 volts, and so on. So that's the primary function of that, and it's uses buck converters to do that. But that thing does not have software. It's a hard logic thing, and it watches the microcontroller. And if it sees the microcontroller restart more than like 5 times in a second, what it does, again, the same thing, it powers off all the 5 physical interfaces for all the networks and shuts the thing down and takes that ECU out of the network. It's the buck stops here, and if we think we're corrupted, what we do is commit suicide.
Yeah, it's an internal threat.
We're an internal threat. So we kill ourselves for the good of the car.
Right. We do have to do we have to go through functional safety audits. And it is exactly as you say, David, where we can't reuse technology, we can't reuse code, can't reuse operating systems, etc. Everything there's a lot of redundant paths, and they're dissimilar. And you know, further to that, and I've also seen this in the telecommunications industry. For example, a telephone switch or a cellular network switch, where there would be an A and a B switch geographically separated, but it isn't in a single master situation. It in fact quite often it alternates between, you know, A to B. A is the master, then B is the master, and it alternates back and forth. And you know, a lot of your database, well, all of your databases are replicated, and those
phone systems I worked on in the 1980s were that way. They switched over at midnight.
Yes.
Yeah, every night they switched to sides so that you wouldn't have a latent failure of thinking you had a backup when you didn't have a backup.
Right, exactly. Yeah. It's like the spare tire in your car. You don't know if you've got air in it until you get a flat tire.
Right, yeah, and then discover your backup isn't working either, right? I love that kind of design. It's just really fun of how you can make the thing so it just can't be killed. And the early on in my career, I did the National Reservation Center for Japan Airlines, and this is pre-internet. And they had a new building in downtown Tokyo, and they consolidated from the 2 airports. and they had a raised floor the size, of like a professional basketball stadium size raised floor, and they had everything in there. And the phone system was the most mission critical, more than the reservation computers. If the reservation computers went down, they could still do it by whiteboards. But if the phone system went down at that time, the revenue was going to the competitors, and it was millions of dollars an hour in 1980s dollars. And they were complaining about our quality and our hardware. And our quality was a little crappy. Our paint jobs weren't quite right and stuff. And then, but they had this thing set up, all this DC, and they had redundant power cables down the different sides of the building. And they had in there, they had batteries for 6 hours and a diesel generator and 100,000 liters of fuel behind that thing. And one day, everything on the floor went down, everything, but our phone systems. And yeah, phone systems did not flinch and kept running. After that, all complaints and quibbles about our quality immediately ceased.
Yes.
That was
communications is so important, even for disaster recovery. And now,
Yeah.
of course, it's hitting the cellular networks, right? We
Yeah.
can't afford to have the cellular networks go down in the event of a natural disaster.
Yeah.
But yeah, how it's a difficult thing to achieve because there's the physical nature of the implementation.
Oh yeah. Yeah, we had the problem in Texas. It actually got us. So we narrowly avoided this, but I was talking to ERCOT about 5 years ago before we had the big storm and killed 200 people because we weren't too prepared enough. I was talking to ERCOT, which is the grid for Texas. Texas has its own grid, only a little bit connected. And he explained to me that their nightmare is black start because beyond 8 hours, everything's batteries run down. And that means to switch, and the electric power network has millions of components in it. And that means to restart from true black condition, you have to roll trucks to every piece of equipment.
Whoa.
To get them instead of mouse clicks from a control center. And the thing that guy predicted, told me about is exactly what happened, which was natural gas is controlled by one group of people and electric power is controlled by another. And 40 or 50 years ago, the natural gas pipelines used to bleed off natural gas to run compressors to pressurize the pipes. But some MBA consultant said, "Oh, that's inefficient. Why don't you just run them on electricity?" So they did. They replaced all that with electric pressurizers. And so when they had the excrement hit the fan, and they were trying to restart power generators. The power generators were saying, "Send us some natural gas," and the natural gas people were, "Send us some power." And it was deadlocked, and it was a mess, and there was a lot of egg on their faces, and people got fired, and they did a lot of changes to tighten that up after that because it was so embarrassing, and of course several hundred people lost their lives too. But yeah, this problem of making stuff resilient is really an interesting design challenge, but you can do a lot without just brute force. The brute force stuff is interesting, but it doesn't work very well on things like a car because the car would weigh 60 tons or something by the time you were done. So you got to do some.
And there's a time and a place, right? I know
Right.
I'm familiar with applications, for example, that need high precision or high accuracy, or they need the perfect solution, and anything short of that is of no use to them. So that's one situation, but then there's the other situation where even a degraded solution is better than no solution, and that's where the resilience comes in, where if and as you say, operating in the presence of your malicious actor, in the presence of that threat. You can't just crawl into your shell.
Yep.
Yeah, just a point, Ivan. Put in a plug for the Resilient Systems Working Group. They are very active. They have weekly meetings that I attend, and they have a very, very nice contribution to the CBOC with a long list of these diverse methods of building redundancy and building diversity in the design for resilience. And now they're in the process of writing a primer and a guidebook, and I think they'll have a lot of really useful ideas about how to design in resilience, not just for cybersecurity, but for every system.
Mhm.
Yep.
There, we've lost a few people, but the few who are still here, would like to hear from you. Any questions or comments or experiences? No? Going once? Going twice? All right. Well, we're at the hour, just past the
Yeah.
hour. We did budget an extra 15 minutes in case there was more discussion, but
Yeah.
I think maybe we'll pull the plug here. I want to thank you, David and Ivan, for a great presentation. I think this was very good, and I see there's some thanks coming through the chat as well. We appreciate the time that you've put in. As a Canada chapter community, it's nice to be able to share some of this knowledge.
Yeah, and if anyone has questions offline, send and drop Ivan or me a note, and we'll talk about it. Right.
Very good.
And
Well, with that,
look forward to an article in Insight magazine.
yes, yeah, be watching for that in the May edition. Is that correct, Ivan?
No, I think it's August. I think
August edition. Okay, so yeah, do watch for that. David and Ivan will be published in Insight in August.
we hope.
We hope. Okay. And also, Ivan Taylor will be presenting at the Toronto in-person event in May. Is that correct, Ivan?
May 24th. Yeah.
May 24th. We're working on making that a hybrid event, but that's not guaranteed yet. But I'm hoping that we can make that a hybrid event so anybody can dial in from across the country and elsewhere around the world, and just to take that bit of time from the in-person event to share with everybody. So we're hoping to make that hybrid. Watch our Canada chapter website for details. As always,
the Toronto in-person event will be on a different subject. It'll be on artificial intelligence for MBSC.
Very good. Okay, thank you, everybody. I'm going to stop the recording.
Okay.